Recording this session, and I will share my screen. Okay, can you see my screen? Can you hear my voice? Any response?
Yes, doctor.
Okay, thank you for the response. Okay, so last week we have stopped until this slide. Am I correct or not? Last week we already learned about this topic, right? Any response for this? Rasanya saya dah tunjuk yang ni Nobody knows? Can someone confirm me that we have stopped until this slide last week? Boleh siapa-siapa confirm?
Ya.
Betul
Betul.
Okay. So last week I have taught about this slide, which is about a single sideband signal generation using phasing method. Okay. So this is the block diagram for the modulator circuit, which is in the transmitter. Okay, so the modulator produce single sideband signal. Okay, so how do we generate the single sideband signal? There are a few methods to use. So this slide is about phasing method. Okay, and for your information, this single sideband signal generation, this slide specifically this slide has been asked previously in the previous semesters. Okay, we have answered this question a few times. Okay, and I have given you the solution. Okay, because in the previous semester we give this same block diagram, and we give the values. For example, the function of modulating signal, and also the function of carrier signal. Okay, and the students are asked to define the equation. For example, here at point A, at point B, at point C, at point D. Okay, so we have asked this kind of question, and then we proceed to ask the student about draw the frequency spectrum. Okay, frequency spectrum. Draw the frequency spectrum, and then we also ask the student to find the parameter of total power, to find the parameter of bandwidth. Okay, so we have asked this in the previous semesters. Okay, so the question is it's not too difficult. It's not difficult actually. Okay, if you understand how the system works, then you can answer the question easily. Okay, and for your information, again, I repeat again, for balanced modulator will do the process of multiplication. Okay, multiplication process. That means it will multiply both of the input. Okay, it will multiply the VMT and also the VCT in time domain. Okay, so VCT this will multiply the VMT. Okay, so you will produce the double sideband suppressed carrier. So balanced modulator will produce double sideband suppressed carrier. Okay, and when you add up both of it, A and B, okay, to produce C, you're gonna see that one of the sideband will be cancelled out. Okay, because of the plus and minus, the difference of plus and minus. So you're gonna produce single sideband without carrier at point C, and then you amplify the amplitude to get the point D. From here you can draw the spectrum and also find the total power. Okay, and the bandwidth of course the bandwidth is equal to the frequency of the modulating signal FM, okay, which is half of the double sideband full carrier. Okay, so we have seen this. Okay, up to this slide, up to this topic is about single sideband signal generation. Macam mana nak generate a single sideband signal. Okay, so we have a filtering method and also the phasing method. Okay, so far in the exam we asked about phasing method, this one. And if we're gonna ask in the future, we will ask also about this topic. Okay, this is one of a good topic to ask in the final exam. Okay. Okay, so AM demodulator. Okay, the next topic is about AM demodulator. Okay, so before this slide, which is up to single sideband, we have learned about the modulator circuit, which is contained in the transmitter. Okay, modulator contains in the transmitter. Okay, modulator ini terletak dalam transmitter. Okay, so within the transmitter, okay, there's a modulator circuit. Okay, which function is to produce the AM signal. Okay, and modulator to generate the AM signal. And let's see what happened in the receiver side. Okay, so demodulator is part of receiver. Okay, demodulator is part of receiver. Okay, so within this receiver there's a demodulator circuit. Okay, which will do the reverse process of modulation in order to get the original signal at the output. Okay, so demodulation is the process of recovering the original signal frequency. Okay, so since we at the transmitter, it will do the process of modulation to convert the modulating signal, the input, which is, for example, my voice. For example, when I call my friend, okay, I will speak through the phone. Okay, I will speak through the phone. So the phone will do the process of modulation to convert my voice into electromagnetic waves, which can be transmitted across the wireless medium. And then that signal travel through the wireless medium, from transmitter to the receiver. The receiver will receive this signal, okay, and then will do the demodulation, which to convert into original frequency signal, which means the receiver receive the electromagnetic waves and then do the process. It will do the demodulation process to convert the received signal into original frequency signal. Okay, so that the other side will listen to the same voice, which is my voice. Okay, so demodulator, okay, here in your slides contains diode detector and also transistor detector. So the word detector here means demodulator. Okay, the word detector here means demodulator. Okay, and later you're going to see that the demodulation process happens at the end of the receiver section, because within the receiver there's a lot of processes happen. Okay, at the end of the process, there's going to be demodulation process before the signal come out as a original signal, okay, which is the BMT. Okay, So the main function of the receiver is to retrieve again, to produce again the same signal of the modulating signal from the transmitter. Okay, that's the job. That's the main job of receiver. Okay, so we're gonna see later about demodulation process of double sideband full carrier. Okay, how we want to retrieve the original signal from the received double sideband full carrier signal. Okay, so diode detector and also transistor detector. Okay, so this is the diode detector. Okay, diode detector. Again, in the modulators topic, you have seen about diode modulator. Okay, previously we have seen about diode modulator and also transistor modulator. Okay, so in the receiver part, we will also see the diode detector and also transistor detector. Okay, so for your information, there are many other types of demodulator, not only diode detector or transistor detector. Okay, in the real world scenario, in the practical world, there are a lot of detector. There are many types of detector. Okay, not only diode and transistor. Okay, so if you see from here, again the diode allows only allows current to flow in one direction only, and that means it acts as a switch. Okay, so you see that from here the input is AM signal, double sideband full carrier. Okay, and it will pass through here this coil, and then the current will flow into one direction only. Okay, so diode prevent reverse bias. Okay, diode prevent reverse bias. So that means during the positive cycle, during the forward bias, the current will flow in this direction. Okay, and at the same time it will charging the RC tank circuit. So this is RC tank circuit, which is equivalent to the LC tank circuit in the previous slides. Okay, so this RC tank circuit will delay the degradation of the signal to the to form the it will produce the other half of the signal during the reverse bias. Okay, so during the forward bias, this RC tank circuit will charging, okay, to a certain amount of level, and then when the current in the reverse bias change polarity, become reverse bias, so this RC tank circuit will discharge to produce the other half of the signal. Similar concept with the modulation process. Okay, and this C2 capacitor will remove the DC voltage, so that the signal will be centered at the axis. So how does the waveform looks like? It shows in this slide. So you see that from here, so originally you receive signal. Okay, originally you receive signal double sideband full carrier. Okay, originally like this. Wait. Okay, so originally you receive signal like this. Okay, this is at the input. Okay, ini pada input. So you receive signal to the demodulator as AM double sideband full carrier. Okay, and then what? And then it's gonna pass through the diode. So what happened is that diode prevents reverse bias. Okay, So that means this is before the diode is like this, double sideband full carrier, and right after the diode, okay, right after the diode, which is maybe I can put point A. Point A is double sideband full carrier, and then at point B, what happened? At point B, the diode will cut off the negative cycle, or it will prevent the reverse bias. Okay, so what happened at point B? At point B, the signal will look like this. Okay, at point B, the signal will look like this. Okay, only half of this, so there's no the above part is not like this, so it only contains this one. I'll show you again. It will contain this one. Okay, this is right after the diode. Half of the double sideband full carrier. Okay, separuh daripada double sideband full carrier waveform. Okay, so this is at point B. Okay, and then what? What happened at point C here? Right after the RC tank circuit. Okay, right after the tank circuit, what happened? Okay, right after the tank circuit, the wave will look like this. Okay, so you see that when the signal wants to go down, okay, the RC tank circuit will delay the transition. Will delay the transition. So what happened is that the waveform will look like this. Okay, instead of going down, it will slowly going down. Okay, it will slowly going down. Okay, it will prevent the transition towards the negative cycle. Okay, so actually the RC tank circuit will top up at this point, and then reverse bias, and then a forward bias, and then RC tank circuit will activate. Forward bias, RC tank circuit will activate, and then forward bias, RC tank circuit activate, and so on. So RC tank circuit prevent the wave from going down towards the negative cycle. Okay, sorry. So it will look like a sawtooth like this. It is like a sine wave, but not smooth. Okay, it is like a sine wave, but not smooth. So this is at point C, right after the RC tank circuit. So RC tank circuit will discharge to prevent the fall of the signal towards the reverse bias. So you see that again, I repeat, this is during the charging process. Okay, so I erase a little bit. So I repeat again, this is during the charging process, and then RC tank circuit will discharge, charging forward bias, RC tank circuit will discharge, forward bias, RC tank circuit will discharge, and so on, sehinggalah until the end. Okay, until the end. Okay, so that means there's no this one, there's no this one. Okay, this is not included in the drawing actually, for part C. Okay, for part C, you're gonna see you're gonna have a sine wave, a sawtooth sine wave like this. Sine wave berbentuk gigi seperti ini, at the above here. Okay, this is at point C. Okay, and then what? And then what, at point D over here, after the capacitor C2, what happened? Capacitor will remove the DC voltage. It allows only the AC voltage to flow. So that means what? You see that the graph now looks like a sine wave above a certain level. Okay, that means the DC voltage here, this is a DC level. Okay, the DC level is here. Okay, so what happened is that this capacitor C2 will remove the DC voltage. That means okay, so that means the wave will drop to the x-axis. Okay, so I will draw the x-axis above here. Okay, so now the wave drops to the x-axis. Okay, the new axis is here. Okay, so the wave drops to the x-axis. That means that the DC voltage has been removed by the capacitor C2. Okay, so the wave centered at the x-axis. Okay, so gelombang itu jatuh pada x-axis kerana DC voltage itu telah remove, telah dikeluarkan, telah diasingkan oleh C2. Okay, so at point D, you're gonna get a sine wave at x-axis at point D. Okay, at point D, you're gonna get a sine wave, a sawtooth shaped sine wave like this, which centered at the x-axis. Okay, so this is actually the VMT actually. So this is actually the VMT, but it is not a smooth sine wave. In order to make it smooth sine wave, we're gonna need another filter to filter up the shape of the sine wave so that it's gonna produce a smooth sine wave at the output like this. Okay, so the output of the modulator is like this, sawtooth like this, but after the demodulator, there's gonna be another filter to shape the sine wave into a smooth signal like this. So at the end, you're gonna produce VMT at the output, similar with the input signal at the transmitter. Okay, sama dengan signal pada transmitter. Boleh So if you are asked to explain, maybe you can explain about this. So this is again at point A. I repeat again, point A, you receive the double sideband full carrier. At point B, you're gonna have half of the double sideband full carrier, separuh daripada double sideband full carrier. At point C, okay, you're gonna see that it produces a sine wave. It produces a sawtooth sine wave, but located at above a DC level. Okay, and the RC tank circuit discharge during the negative cycle or during the reverse bias of the diode. So it prevents the signal from drops towards the negative cycle. Instead, it will slowly discharging, slowly the process of signal drop. Okay, and then the current will change into forward bias, so it will charging again, and then discharge, and then charging, discharge, and so on. Okay, so this is at point D, and then after point D, it goes through the capacitor C2. Capacitor C2 will remove the DC level, so the signal drops towards the drops at the x-axis, so centered at the x-axis. Okay, so at point D, you're gonna get a sine wave, a sawtooth-like sine wave centered at x-axis. And in order to get the smooth waveform of VMT, we need another filter to shape the smooth sine wave at the output. Okay, So for your information, we haven't asked this question in the final exam yet. Okay, belum pernah ditanya dalam final exam about this process. Okay, if you are asked, explain the process happens inside the double sideband full carrier demodulator. So you can explain the steps from A, B, C, D. Okay, macam mana how the waveform looks like in process A, process B, C, and D. Okay, we have asked about the modulator in the previous slides, but we haven't asked about the demodulator yet until now. Okay, so you need to be able to explain briefly about each process, A, B, C, and D. You can draw, you can sketch how the waveform looks like in process A, B, C, and D. Okay. And then this is the transistor detector. Okay, similar concept with the diode detector. The input is here, which control the base of the voltage. Okay, so this is the input is controlled by the R1 and R2, and this input determine the voltage at the base of the transistor. So if the voltage at the base more than the threshold voltage, that means the current can flow from the collector to the emitter to the ground. Okay, otherwise it will switch off. And here we have the Roc Tank Circuit. Okay, which will produce, which will discharge during the reverse bias of the transistor. Okay, so during the reverse bias of the transistor, it will discharge and provide the other half of the output. Okay, and then C3 will remove the DC level so that the output signal is a sine wave, or the original signal, which centered at the x-axis. Okay, so this capacitor remove the DC voltage. And then what? DSB, double sideband suppressed carrier, and single sideband demodulation. Okay, so for double sideband suppressed carrier and single sideband demodulation process, so this is the block diagram. Okay, so you see that from here we have the input upper sideband. Okay, we have the input upper sideband USB of the single sideband. So we receive upper sideband from the SSB signal, put inside the balance modulator. Okay, and we inject the balance modulator with the same carrier signal. Okay, so this oscillator produce the same carrier signal as in the transmitter. Okay, so that means we inject, so we inject the balance modulator with the carrier as well as the input signal. Okay, so that means the receiver needs to know what is the carrier frequency, what is the resonant frequency. So this is actually what we call as the resonant frequency. Oscillation, the oscillator will oscillate at resonant frequency, which is the carrier frequency. Okay, because we want to capture the signal that center at the carrier. Remember that when we send the signal from the transmitter, the signal is actually centered at the carrier frequency. So that means when we want to recover the signal, we need to make sure that it is resonant at the carrier. Okay, when we mention about resonate at the carrier, that means the center would be at the carrier. So that's why we inject with the carrier frequency in the balance modulator. So this is in the receiver. Okay, guys, when you see that, when you see this balance modulator, this is actually part of the demodulator. Okay, all of this is part of demodulator located in the receiver. Okay, not only balance modulator in the transmitter. Tidak semestinya balance modulator itu ada dalam transmitter sahaja. Okay, so all of these located in the receiver. Okay, so it uses the concept of balance modulator at the first part to do the modulation actually, to mix up, to modulate the input single sideband with the carrier. So we do the multiplication process in time domain again. Okay, so remember when we do multiplication in time domain, we're gonna produce additional two sidebands, upper and lower. Okay, remember previously when we multiplied two inputs, it will produce two sidebands, upper and lower. Okay, so what happened here? You see that this is the input. Okay, so this is FC plus FM, which is from the input, plus FLO, which is this one, the local oscillator frequency. This is the upper sideband, and then the parameter here is FC plus FM minus FLO. Okay, so since FLO is equal to the carrier frequency, so that means we can cancel out the carrier frequency for example like this one, so we get like this, FC plus FM plus FC, which is a upper frequency, and we get also FC plus FM minus FC for the lower sideband. Okay, so this one is 2FC plus FM, which is high frequency, and this one is FM, which is low frequency. Okay, so we can use low pass filter to select only the low frequency, which is this one. Okay, so we get the output is low frequency, which is the message frequency or the modulating signal frequency. Okay, so at the end we're gonna get again the VMT at the output. Okay, so I want to explain again. I want to explain that how your lecture notes explain about the process in the receiver. Okay, because starting from this slide, we are actually learning about the receiver process. Okay, starting from this slide, we are learning about the receiver process. But your lecture notes focus about the end process in the receiver first. Okay, so wait, maybe I can draw. I want to draw so that you can have a more understanding. Okay, so let me draw a receiver block diagram like this. For example, this is receiver, for example. Okay, so this is receiver. Okay, so receiver. So diode detector is actually the end process of the receiver over here. Okay, there are many other process happens here. At the end is the demodulation or detection process. So your notes start from the detection process or demodulation process at the end. Okay, so I hope that you are not confused. We are not learning from the front side. We are learning the main part at the end. Okay, which is the demodulation process. Okay, and this is similar, the end process, demodulation process. Okay, so starting from here, your lecture notes, these lecture notes explain about the front process, okay, which is the filtering process. So maybe I can draw again so that you can have better understanding. Okay, where are we now? Okay, where are we now? Assume that this is the receiver. Assume that this is a receiver. Okay, So we have seen about the demodulation process previously. Okay, now your lecture notes wants to explain about the front process, which is the filtering process. Okay, because the antenna receive many signals, so we need to filter up. Okay, we need to do the filtering process to remove the unwanted signals. Okay, so this is what we call as a filtering process, which contains the tune circuit. Okay, so tune circuit consists of filtering circuits which select only the desired frequency band and remove the others. Okay, so starting from this slide is about tune circuit actually, which shows the parameter of the main parameter of the filters. Okay, so let's look in this slide, which is among the important parameters within the receiver. One of it is the selectivity. Okay, selectivity is the ability of the receiver to select the desired frequency signal and remove the others. Okay, that's the selectivity. So selectivity is determined using a certain parameter, what we call as the shape factor. Okay, so shape factor is equal to bandwidth of minus 60 dB divided with bandwidth of minus 3 dB. Okay, so for your information, this shape factor is related to the filter parameter within the tune circuit. Okay, if your tune circuit has a good filtering process, it will select only the desired frequency and completely remove the unwanted frequency. Okay, so for example, like the shape factor SF. Okay, shape factor has no unit because we divide hertz and hertz. Bandwidth is in terms of hertz. We divide hertz and hertz, so there's no unit, and we can express this in terms of decibel. Okay, so ideally we want the shape factor to be towards equal to 1. Okay, towards equal to 1. That's the best case scenario. Okay, if the bandwidth of the minus 60 dB equal to the bandwidth of minus 3 dB, which is not happen in the real world, okay, ideally we want it to be close to 1. Okay, so how does it looks like? So I will skip one slide to go to this part. Okay, this is the frequency transfer function of the filter within the tune circuit. Okay, this is the frequency response curve of the filter in the tune circuit. Okay, so this is the general curve of the frequency response curve, okay, which is like a bell shape like this. Okay, above here is 0 dB and then minus 3 dB is here. So minus 3 dB is this dotted line. Okay, and minus 60 dB is somewhere here, minus 60 dB. So you see that the line cross for minus 3 dB, it cross over here. Okay, and minus 60 dB somewhere over here, it will cross at this point. Okay, so you see that minus 3 dB, okay, it cross at frequency F1 and F2. Okay, it cross at frequency F1 and F2. Okay, and minus 60 dB, it cross at frequency for example F3 and F4, for example. for example, okay, for example. So you see that ideally, okay, ideally we want the because this is the center here is a resonant frequency, the center frequency of the signal that we want. Okay, this FR here is a resonant frequency, which is the center of the frequency band that we want to process. Okay, ideally, okay, ideally we want the filter to be able to capture this part. We want the filter to have a very sharp cut off like this, like a square box like this, ideally. However, in the practical case, in the practical scenario, the filter is not have a sharp, very sharp like this. Instead, it's gonna have a circuit like this, slope like this. Okay, but when we want to design the filter, we want to design a filter that has a very steep slope. Okay, we want to design a filter that has a very steep slope. Okay, the steeper the slope would be better, so that we can remove the unwanted frequency, because we don't want any frequency over here. Okay, we don't want any frequency over here, we just want in the middle here, ideally. Okay, so the steeper the slope would be the better of the filter would be a better filter. Okay, lagi cerun, lagi curam dia punya slope itu, lagi bagus, because we can remove the unwanted frequencies. Okay, so remember, when we want to design filter, we try our best to design a filter that has a very steep slope. Okay, if the slope is not steep, it is not a good filter. Okay, because the wider the slope, the wider the curve, we will capture many frequencies in the system. Okay, lagi lebar dia punya skirt tu, slope tu, lagi banyak frekuensi yang dia akan capture. Okay, so that means the steeper the slope is better. That means we want the filter, the filter to be able to capture, to be able to towards ideal case, which is like this, ideal case. Okay, so that's the issue of filtering process. Okay, ideally we cannot, okay, secara ideal, ideally we cannot produce this kind of a filter very sharp like this, cut like that. Okay, it will have a skirt or a slope like that too, which will include a small harmonics of signals. Okay, but that one is insignificant. Okay, because if you have a very steep, that means the amplitude of the harmonics will be smaller in the skirt. Okay, the harmonic will be smaller in the skirts, so we can remove that using a few set of filters, using a few set of filters. Okay, not only one filter, we're gonna have more than one. Okay, so ideally we want the shape factor to be close to 1, towards 1. Okay, if not ideal, in the non-ideal case, it is less than 1. Okay, it is less than 1. Okay, so I go back to the slide. Okay, so this can be expressed in terms of decibel. So if you want to express in terms of decibel, that means 10 log of SF. Okay, 10 log of SF you get in terms of decibel. Okay, and another parameter is the bandwidth of the tune circuit. Okay, so this is the bandwidth of the tune circuit, which can be calculated based on the resonant frequency, the center frequency of the filter, divide with the quality factor. So the quality factor is equal to inductive reactance divide with resistance. So this is actually ohm divide with ohm. Okay, so this XL is not a size of a shirt, dia bukan size baju. So XL here is a 2 pi f, 2 pi f, or 2 pi f, 2 pi fr, 2 pi f resonance, or you can say that omega L, 2 pi f, okay, omega L, okay, or omega L, okay, omega is 2 pi f, okay. So Q no unit, okay, Q has no unit, bandwidth in term of hertz, okay. So normally in the question when we ask find the selectivity parameter, normally it is referring to the Q parameter. Okay, dalam in your lecture notes, in the example, when it mentioned about the selectivity parameter, it is asking about Q parameters. Okay, because selectivity has a few parameters: the Q parameter, the bandwidth of the tuned circuit, and also the shape factor. So there are actually 3 parameters for the selectivity under the selectivity topic. Okay. So we're gonna see about the example about how to find the values for this one. The bandwidth of the tuned circuit, the quality factor of the tuned circuit, and also the shape factor of the tuned circuit. Okay. And then what? Other than selectivity is the sensitivity parameter. So sensitivity parameter is the minimum RF signal that can be detected at the output of the receiver and still produce the usable demodulated info signal. Okay, so when we receive the signal, okay, okay, so the signal that arrive in the receiver has a low amplitude, because the signal has traveled from transmitter to the receiver at long distance. It has been attenuated many times. So the signal arrived at the receiver has a low amplitude. So the ability of the receiver to detect that low amplitude signal and still can produce a good output. This is the referring to the sensitivity parameter. Ideally, we want the receiver to be able to detect a small amplitude of input signal and produce the best output. Okay, that's the best case scenario that we want. Okay, and then what? Bandwidth improvement factor. This is the third parameter, bandwidth improvement parameter, which is equal to so this is related to the tuned circuit, which is equal to bandwidth of RF divide with bandwidth of intermediate frequency, IF. Okay, so this is in term of hertz divide bandwidth in term of hertz. Okay, this is higher than that. Okay, so you're gonna see later that the bandwidth of RF is larger than the bandwidth of IF. Okay, how does it looks like actually? So when we draw the spectrum, so let me draw the spectrum so that you can have better understanding. Okay. Okay, so for example, this is voltage versus frequency, for example. And if you remember that, wait. Okay, if you remember, okay, initially we have the input message modulating signal frequency, okay, and then when we do the modulation process, we are actually translate the frequency into higher frequency, which is FC. This is okay, this is FC plus FM, FC minus FM. Okay, So when we do the modulation process, we are actually translating the frequency into a higher frequency which is suitable for transmission. And when these signals arrive in the receiver, we want to do the demodulation process to get the original frequency signal. But in the receiver, it is not directly converted into modulating signal frequency. Instead, it will down convert the frequency into intermediate frequency. How does intermediate frequency looks like? So it will looks like this. Okay, so we have here FIF center, okay, and then here is FIF USF, upper side frequency. Over here is FIF LSF, lower side frequency. Okay, because this one, okay, FIF center, the center would be at 455 kilohertz. Okay, FIF center, we're gonna see later about this. FIF center is equal to 455 kilohertz by standard. Okay, and this component, this part is what we call as the intermediate frequency. Whereas, wait, maybe I use a different color. Wait. Okay, so this part is what we call as the intermediate frequencies. Okay, and this part is what we call as RF frequencies, RF band. So before, okay, this is what we call as a down conversion. Okay, down conversion happens before demodulation process. Okay, so in the receiver will down convert from RF frequency band. What is RF frequency band? RF frequency band is the AM band, which is, as I mentioned previously, between 5xx kilohertz until 17xx kilohertz. Okay, and receiver will down convert into intermediate frequencies center at the 455 kilohertz by standard. Okay, and then this will be passed to the demodulator, which will do the demodulation process to produce a single frequency output, which is the modulating signal frequency. Okay, so what is the bandwidth of the RF? Okay, so the bandwidth of RF is this one. Okay, and bandwidth of the IF is this one. Okay, so you divide this one, so you get a value without a unit, no unit, and you can express this one in terms of logarithmic, which is 10 log of bandwidth improvement, so which is defined as the noise figure improvement. Okay, noise figure improvement. Okay, yeah. Okay, noise figure improvement. 10 log BI, 10 log bandwidth improvement, so you get this in terms of decibel. Okay. Okay, so let's go through the example. Example. This one, So this is an example about the tune circuit, the process that happens at the front side of the at the front end of the receiver. Okay, the front end of the receiver. The front end of the receiver, as I mentioned earlier. Okay, so this is the receiver. Okay, so this is the tune circuit. Okay, the detector circuit is at the back side here, okay, at the back end. Okay, so this is example about tuned circuit. Okay, so it said that a high Q tuned circuit is used to keep the bandwidth narrow to ensure that only the desired signal is passed. So tuned circuit is very important so that we can select only the desired band so that we can do the next process. Okay, so assume that the 10 microhenry of coil with resistance of 20 ohm is connected in parallel with the 101 picofarad of the capacitor. Okay, so the circuit resonate at what frequency? So you can sketch the circuit. How does the circuits look like? This is a very simple circuit like this. Okay, so the L and C is connected in parallel. Okay, so we have here L and C. Okay, so here we have so we have another one here is a resistor R, L and C. Okay, so assume that coil with resistance is connected in parallel with the, okay, so this is also R, L and C. Okay, so you see that L and C is in parallel. Okay, L and C is in parallel. Yeah, it is actually like this. R, L and C. So L and C is connected in parallel. So what we can find the first question is this. Find the resonant frequency Fr. Okay, so Fr is equal to resonant frequency is equal to 1 over 2 pi square root of Lc. So this is how to find the resonant frequency. Okay, you put inside the L parameter in Henry, C parameter in Farad. Okay, so put inside the parameters and you can get 5 megahertz. Okay, you can try now. Try now using your calculator. Okay, so 10 microhenry multiplied with 101.4 picofarad. You multiplied both of these and then square root, and then multiplied with 2 pi, and then 1 over the answer, and you get 5 megahertz. Boleh cuba So I think the value is not exactly to 5 mega. So in your lecture notes, it has been rounded up to 5 megahertz. Actually, it is I think it's 4 point something or 5 point something. So it is not exactly 5 megahertz. So in your notes, it has been rounded up to make it easy for you to understand. Okay. And then what? What is the inductive reactance? So inductive reactance is this one, which is 2 pi F resonance. 2 pi F resonance, 2 pi FL. So put inside the value. Okay. So 2 pi multiplied with 5 megahertz multiplied with 10 microhenry. Okay, from the question. So you will get 314 ohm. Okay, 314 ohm. And then what? Then the question said that what is the bandwidth of the tuned circuit? So the bandwidth of tuned circuit, this one. So the bandwidth of tuned circuit is equal to inductive reactance divided with the inductive reactance divided with the resistance. Okay, so inductive reactance divided with the resistance. Okay, both of it in terms of ohm. So you put 314 divided with 20 ohm. Okay, 314 divided with 20. So you get 15.7. No unit. Okay, no unit. Oh, so I think I wrongly asked this one. Sorry. So actually this one what is the selectivity of the circuit? Okay, sorry. What is the selectivity of the circuit? So here, in this example, this example actually wants to find the Q parameter. Okay. This example should explicitly mention about the Q parameter, so that easy for the student to answer. Okay. If we ask in the final exam, normally we will straight away ask the student what is the quality factor. Okay, because selectivity contains Q factor, the bandwidth parameters, and also the inductive the other parameters. You see that previously we have Q parameters, bandwidth parameter, and also the SF. This is under the selectivity. Okay, but for this example, it is referring to the Q factor, Q parameter. Okay, so if you ask me, it is better to write a question that is explicitly mentioned about what you want to ask. Okay, so it is here in this example, it is asking you to find the Q parameter. Okay, and then find the bandwidth of the tuned circuit. The bandwidth of the tuned circuit is equal to resonant frequency divided with the quality parameter. Okay, quality factor. How much? So 5 megahertz divide with 15.7. So 5 megahertz divide with 15.7. So you get 318.47 kilohertz. Okay, try to use your calculator to find the answer. If you can get the answer, that means it's good. Okay, cuba gunakan calculator anda sekarang. Okay, so this is the bandwidth of the tuned circuit. Okay, so you see that from this picture, I want to show you from this picture. From this picture, you see that the antenna is capable to receive the whole AM bandwidth, and including other frequency as well. Okay, and the tuned circuit will limit the frequency band that we want to process in the receiver. Okay, so let's say that ideally, let's say that the receiver, the antenna receive frequency from 57xx kilohertz. Sorry, 57x kilohertz. The entire AM bandwidth. For example, the antenna is capable to receive the entire bandwidth of the AM. For example, from 57x until 17xx kilohertz. Okay, so the receiver, for example, the tuned circuit will limit the frequency band. So this is how much? This is more than 1 megahertz of bandwidth. Okay, from 57 kilo until 17 kilohertz, 1700 kilohertz. So you get more than 1 megahertz of total bandwidth of the AM. For example, you receive all of it, but the tuned circuit will limit the amount of bandwidth that we want to process. Okay, for example, the tuned circuit limit up to 100K only, for example. Okay, so if I draw the frequency band, okay, if I draw the frequency band like this, so that you can have better understanding. So the antenna receive all of this. Okay, and the tuned circuit will limit the frequency band that we want to process. Maybe something over here, something like this. Okay, and remove the others. Okay, so we want to select only a small portion of the bandwidth only. Okay, okay, so the next question asks, find the upper and lower cutoff frequency of the tuned circuit bandwidth. Okay, so tuned circuit bandwidth, so how much is this? F1 and F2. Okay, this is the bandwidth of the tuned circuit, and how much is the upper and lower cutoff frequency? Okay, we know that the center is FR, resonant, center at resonant frequency, and we already calculate the bandwidth in the previous question, okay, which is 314 kilohertz. So we can find the upper and lower. Okay, center here is 5 mega. Okay, and we get the bandwidth around 314 kilohertz. 314 kilohertz, sorry, 318 kilohertz, this one, the bandwidth. So we can calculate the upper and lower cutoff. Okay, so the solution is that we divide the bandwidth, we divide the bandwidth into two, so that we can get half portion and half portion. We can get how much is this? How much is the half distance over here, and how much is the half distance over here? Okay, so that we can do 5 plus half of the bandwidth, and also 5 minus half of the bandwidth, in order to get the upper and lower frequencies. Okay, so when we divide the bandwidth into 2, we get 0.159 megahertz. Okay, half of it. So half of the distance from the resonant frequency, the center. So we can find the upper frequency is resonant frequency plus half of the bandwidth, separuh daripada bandwidth tadi, which is this one, resonant frequency plus half of the bandwidth, we get the upper frequency. And for the lower, we minus with the FR minus half of the bandwidth. Okay, FR minus half of the bandwidth, we get the lower cutoff frequency of the tuned circuit. For the upper cutoff frequency is 5 megahertz, which is the FR plus half of the bandwidth, so we get upper cutoff frequency of the tuned circuit. Lower, lower cutoff frequency, FR minus 0.159, so we get 4.841 megahertz. Okay, so do you have question to ask? Please ask question now. Okay, if you don't understand, please ask question. Okay, please ask question. Yeah.
I don't understand why we need to plus with FR.
Question number 5.
And lower.
This one,
to find the upper and lower.
Okay. So it is actually like this. So when you in the first question, you find the resonant frequency, FR, which is 5 megahertz. Okay, and then you already found the bandwidth. So the bandwidth is this one. So the bandwidth is 318.47 kilohertz. Okay, so the question asks how much is lower cutoff F1 and the upper cutoff frequency F2. So macam mana nak cari nilai F1 dan F2? We already know FR, we already know the bandwidth. We want to know the upper and lower. Okay, the boundary. Okay, so that's why in this example, first we want to find a half of it. Why we divide with 2? We divide with 2 because we want to know how much the distance over here, so that we can do plus and minus. Okay, kita bahagi dua bandwidth itu supaya kita tahu jarak separuh. Nanti kita boleh tahu cut off frequency. We can find the cut off frequency by adding and subtracting from the resonant frequency. So F2 is equal to FR resonant plus the half of the bandwidth, okay, which is 318.47 divided with 2. Similar with the lower cutoff frequency, FR minus 318.47. Okay, am I answering the question?
Yes, sir.
Okay.
Understand.
Any more question? You can ask. If you have other question, you can ask, no problem. Kalau ada soalan lagi nak tanya, silakan silakan. Okay. Later you're gonna see that. Okay, later in the next in the upcoming example, you're gonna see that. Maybe I can use this picture. Okay, you're gonna see that. For example, the antenna received the whole AM bandwidth. For example, we receive around maybe we receive 50 radio channels. For example, antenna able to receive 50 radio channel, for example. Okay, then this will pass through the tune circuit, because when I want to listen to a radio channel, I only listen to one radio channel. I am not listening to 50 radio channel simultaneously. Okay, apabila saya nak dengar radio, saya tak dengar 50 radio station serentak. Okay, so what the receiver will do is to cut to remove the unwanted frequency band. That means we reduce the amount of frequency band so that easy for us to do the next process, signal processing. So what the tune circuit will do is that it will only select, okay, a certain portion of the bandwidth. Okay, so when the tune circuit select a certain portion of bandwidth, it might contain a few radio station, not only one radio station. Bukan hanya satu radio station. So the tune circuit may be able to select not only one radio station, but maybe more than one. For example, the tune circuit select 3 radio station. Okay, from that frequency band. That frequency band consists of 3 radio station. For example, contoh okay. So initially the antenna received 50 radio station, which is too big for the signal processing at the receiver. So the tune circuit will limit the amount of bandwidth, for example, a certain portion, and that certain portion consists of maybe one or more radio stations. Okay, it is not yet one radio station. Okay, because when we want to do the demodulation, we will focus on only one frequency band. Okay, so I will show the example about this later. Okay, so once the tune circuit select, for example, 3 radio station, the next process will process until we get a single frequency band. Okay, kamu cuma nampak, you only see up to tune circuit yet. Okay, we are not moving to the next process. So there are many other processes after this. Okay, so when we can manage to limit the frequency band, easy for us to do the next process until we do the demodulation process. When we want to do the demodulation process, we will modulate only a single frequency band. In your syllabus, we only demodulate a single frequency band. Okay, so we will see about this later. Okay, so the purpose of a tune circuit is to limit the bandwidth. Okay, so that easy to do the next process. Okay. Okay, so now so where are we now? Okay, so where are we now? So if I redraw again, I redraw again so that you can have better understanding about the flow in your notes, so that kamu boleh nampak macam mana flow dalam nota kamu, Okay, so if I redraw again about receiver, because we are learning about receiver. Okay, so this is receiver. So at the beginning we learn about the process over here at the back at the back side, at the back end, and then this is about the detector circuit, detector circuit or demodulator circuit over here. And then you learn about the process at the front end here, which is the tune circuit. Okay, the tune circuit is here. This is a demodulator. Okay, so now now in this slide wants to show you what are the types of AM receiver. It is the type of AM receiver. Okay, as a whole. Okay, apakah jenis-jenis AM receiver? So now we want to see the type of receiver. So ini belum selesai lagi, so there are many other process happens here. Okay, there are many other process happens here. So before your lecture before your notes explain about the other process, it shows about the type of receiver. Okay, sepatutnya yang ini di bahagian awal lagi lebih bagus mungkin explain about type of receiver, and then we go through one by one. Okay, so this slide explain that there are two types of AM receiver as a whole. Okay, this is a receiver. So we have a TRF and we have a super heterodyne, super head. Okay, so tune RF receiver, the simplest type of AM receiver, which is tune RF receiver. Okay, it is a simple circuit, limit to single channel low frequency applications, high sensitivity, and has a few disadvantages. The bandwidth is inconsistent and varies with center frequency when tuned to over a wide range of frequency band. Instability due to large number of RF amplifiers, and the gain is not uniform. So these are the disadvantages of tuned circuit. Okay, so we have tuned circuit, tuned RF circuit. We have tuned RF receiver, and the other one is super heterodyne receiver. Okay, so this is the first receiver type. The second receiver type, before that, tune RF receiver is like this, looks like this. Okay, so it has how many section is this? Two section only, RF section and detection section. Okay, RF section and detection section. So RF section consists of many RF amplifiers to amplify the input. Okay, and then it will do the demodulation process. Okay, so the process is very simple, only involve just a few processes only within the receiver. Okay, so this tune RF receiver is not widely used in many applications, only a certain applications. And if you want to know what are the most application used, they use the super heterodyne receiver, which is this one. Okay, so super heterodyne receiver is the second type of receiver, AM receiver. Okay, so the word heterodyne means of mixing two input. Okay, so the word heterodyne means mixing, so it uses the concept of mixing, and it consists of many phase of blocks, block diagram. Okay, many phases of process like this. Okay, so this is the super heterodyne receiver, which consists of a few processes. Okay, a few sections. Okay, the first one is RF section, mixer converter section, IF section, and also detection section. Okay, over here is a detection section. Okay, so I will explain to you one by one. Okay, so you see that from this part, you already learn about detection section, which is the diode detector and also the transistor detector, which is located over here, audio detector. And you have learned about the tune circuit, which is this one, the tune circuit, or what we call as a preselector. Okay, and you haven't learned about this part. So I will explain to you. Okay, I will explain to you. Okay, so for your information, we haven't asked the student yet to explain about the process happen at the super heterodyne receiver. Belum pernah ditanya kepada pelajar untuk menerangkan proses yang berlaku dalam super heterodyne receiver until now, until last semester. Okay, and this semester I don't know yet. I don't know. I haven't done the question yet. Okay, so I will explain to you. Okay, so that you can take note. Maybe you can take note of the additional information that I will explain to you. Okay, so the first section is the RF section. Okay, RF section consists of tune circuit. Okay, so maybe we can start. Wait. Okay, so RF section contains of preselector, or what we call as the tune circuit. Okay, which select only the desired band of frequencies and remove the others. Okay, because the antenna receive a wide bandwidth of frequencies. So when it goes through the preselector or the tune circuit, it will only select the desired frequency band and then amplify the signal so that we can do the next process. Okay, so the next process is mixer converter section. Okay, and you see that in this example, in the mixer converter the mixer converter consists of two input. Okay, one from the RF section, okay, one from the RF section and another one from the local oscillator. So this local oscillator is gang tune, which is tuned together at the same time. Okay, gang tune means tuning to the same frequency. Okay, which is the resonant frequency. So both the preselector and the local oscillator tune at the resonant frequency, which is equivalent to the carrier frequency actually. Okay, so what happened in the receiver converter section? What happened? It will down convert the signal into intermediate frequency signal. Okay, and the explanation is here. Okay, mixer converter will down convert the RF. What is RF? RF is the AM frequency band. Okay, AM frequency band. Okay, convert into intermediate frequency band, but the shape of the envelope remains the same. Information is conserved, bandwidth is unchanged in this process. So the output of the mixer is infinite number of harmonics and cross product. Okay, because we do the multiplication process. Okay, you see that the symbol is X over here, means that it will do the multiplication in time domain. Okay, so when you multiply input and oscillator frequency, you will produce upper and lower frequency. Okay, so you get the output here consists of Fi, Fo. You get here is the upper sideband, and here is the lower sideband. The OR here means that whichever give you the positive frequency. Okay, normally the local oscillator is higher than the input frequency. Okay, so you get Fi, Fo, the upper sideband and the lower sideband. Okay, and then the tuned circuit filter will select only the desired frequency band and remove the harmonics. Okay, so how does it looks like actually? How does it looks like? Okay, before that, okay, so when we convert into intermediate frequency, okay, it is said that here the local oscillator frequency is usually higher than the RF. RF here is the AM frequency band. Because up conversion leads to a smaller tuning range. Smaller ratio of maximum to minimum tuning frequency, much easier to design oscillator that tunable over a smaller frequency ratio. So when we okay, if the mixer and LO single state is called as a converter, okay, so this is no problem. So this is the center of the intermediate frequency that we're gonna produce. Okay, so it is why it is this is the value by standard. Center of intermediate frequency is by standard is 455 kilohertz. Okay, so why the value is chosen 455? Because it is adequate value. It is enough for selectivity, because it is difficult to design sharp bandpass filter in the center frequency is very high. So the frequency 455 kilohertz is not very high. It is in the intermediate band. Okay, it is not too high, it is not too low. Okay, so that's why the value 455 is chosen. So the center frequency is fixed and factory tuned. Okay, that means when you buy the hardware is designed such a way that when you convert into intermediate frequency, the center would be at 455 kilohertz. And this will effectively suppress the adjacent channel interference because of its high selectivity. So now I will draw so that you can have better understanding about what happened here. Okay, what happened here actually. So okay, so maybe I will draw the spectrum. I will draw the frequency spectrum so that you understand what actually does this notes explain about. Okay, what is this about? So I will draw for you. Okay, okay, so okay, so this is a mixer converter section. Okay, so because when you here when you maybe I can draw here. So when you receive from the antenna, which consists of very big bandwidth, larger bandwidth, and then this goes through the pre-selector. Pre-selector will select only a portion of the bandwidth, for example up to here, for example, okay, and this is can be redraw. I redraw again. Sorry, I need to delete this one. Okay, sorry, maybe I need to redraw again. Sorry, wait. Hope that you can understand this. Okay, so remember that I told you that antenna receive larger bandwidth, very big bandwidth, and then pre-selector will select only a portion of the bandwidth. Okay, so this is the all of this is the RF. RF is the radio frequency band that we receive from the antenna. Okay, so so from the pre-selector, for example, we receive we select this frequency band, for example. So for example, we select this is F resonant, this is F USB, this is another one is F LSB. F USB and F LSB. Okay, so this is RF. So this is the RF. Wait, so maybe I can draw like this. Okay, so this is the RF. Okay, RF again. RF is within the AM frequency band, kilohertz. Okay, this is within the AM frequency band, and this will down convert by the converter. Okay, so the converter will down convert into intermediate frequency. Okay, so this is FIF center, and here is FIF LSF. This is, sorry, USF and USF. This is here FIF LSF. LSF is the lower side frequency. USF is upper side frequency. It's like a upper sideband and lower sideband actually. Okay, and center here is actually 455. 455 kilohertz. So here is 455 kilohertz center. Okay, so this is the mixer converter will down convert from RF frequency band into IF frequency band. Okay, so this is happens done by the converter. Okay, mixer converter will convert into intermediate frequency. Okay, center at 455 kilohertz, which is the standard center frequency for the intermediate frequency. Okay, and here high side injection and low side injection. So we are still in the converter section. So this is just a term. This is just a term about the conversion process. High side injection and low side injection. What is this actually? So high side injection is a term we use to show that the local oscillator frequency is larger than the RF frequency. Okay, if the local oscillator frequency lower than the RF frequency, okay, it is the frequency is calculated as FRF minus FIF. Okay, so these two terms is normally we use to show that where either this is a high side injection or low side injection. Because if we consider this a high side injection, that means we need to use this equation. If the process is low side injection, we can use this equation. So this equation is to find the value of local oscillator or the intermediate frequency. Okay, so because we want to know, we want to find this one actually. We want to find the value of this actually. Okay, so we need to know whether the process is high side injection or low side injection. Okay, normally most of the time in the practical case we use a high side injection. Okay, as mentioned in the previous slide, FLO is usually higher. Okay, so this is normally high side injection. Okay, and then what? So we have seen about this. Okay, what is the mean by term high side and low side injection? So I already explained about the answer to these questions. Okay, so high side injection is when RF frequency when the local oscillator frequency higher than the RF frequency. Okay, that means local oscillator is higher than the local oscillator frequency. So here for the low side injection is when the RF frequency band higher than the local oscillator frequency. So that is the high side and low side injection. So no problem, okay, tak ada masalah. It's just a matter of concept, concept of high side and low side. Ideally, normally we use a high side injection. And then what? So after this, it will go through the IF section. Okay, if you look into the picture, into the block diagram, okay, after the mixer converter, it will go through the, so after this process, up to here, okay, up to here, we already convert RF into intermediate frequency. Okay, but the frequency band that we produce, but the frequency band that we produce consists of a few channels, a few radio station. Okay, it still consists of a few radio station at this point, before the IF section. Okay, before the IF section, although we already convert into down convert, we have do the down conversion, it still consists of a few radio station, more than one channels. If I want to listen to radio station, I only listen to one radio station at a time. Okay, bila saya nak dengar radio station, saya tak boleh dengar semua sekali serentak. Saya nak dengar satu sahaja. Okay, and we need to reduce this into one single frequency channel only. So this comes the IF section. So IF section want to limit again the frequency band so that we only produce single output frequency. Okay, so the output here is the single output frequency, a small bandwidth of channel, a single channel. Okay, I can say that this is only a single channel. Okay, a single channel which center at the 455 kilohertz. Okay, for example, here one channel. For example, here this one, for example, we initially have 3 channels. For example, we have more than one channels, and then after the IF section will produce a single output channel. Okay, and then what? It will do the demodulation process. So when we have a single channel, we can do the demodulation process to produce the VMT at the output. Okay, to produce the which is the VMT at the output. Okay, so in the IF section, sorry, I forgot to explain. Okay, so how does from 3 channel to 1 channel, how does it possible? Because we have the bandpass filter. Okay, so the bandpass filter will select only one channel. Okay, so we receive a few channel, for example 3 channel. The bandpass filter will limit the bandwidth that we desired to become one channel only. So this bandpass filter will make sure it will produce only single channel at the output. So this bandpass filter has a sharp cutoff. It will cut off and produce only single output frequency channel. Okay, and then we amplify it. Okay, IF amplify, we increase the amplitude. Okay, and then put inside the audio detector. We do the demodulation process, and then we amplify the output, and then pass through the speaker. Okay, and this is the IF amplifier. Okay, after the IF bandpass filter, and then we do the demodulation process in the demodulator, and then we amplify the output signal, and then we pass through the speaker. Okay, we pass through the speaker. Okay,
Doctor?
so yeah.
Sorry, for the bandpass filter, macam mana dia nak tahu which kind of channel that the bandpass filter should choose?
Okay, so actually the channel that we want to choose is actually the center frequency. Okay, for example, like this one. For example, nanti ada example. There's gonna be another example after this. Wait. For example, here is for example, here I have a 3 channel. So for example, channel 1, channel 2, channel 3, for example. Okay, and the bandpass filter will tune to the center frequency of the channel that we desired. Okay, for example, I want to select channel 1. So the bandpass filter will tune to this center frequency band of the channel 1. Okay, so it will tune to this frequency and remove channel 2 and channel 3. Okay, so how does the bandpass filter will select? It will tune to the center frequency of the channel. Okay, dia akan tune pada center frequency of that channel. Then you will get that channel frequency.
Let's say I want the second channel, so it will tune at the center of the
Yeah,
second channel
it will tune to this center frequency.
and remove the 1 and 3.
Yes.
Okay. Okay.
For example, I want to listen to radio station number 1. So remember that when you want to listen to radio station number 1, when you want to listen to radio station number 1, you are actually tuned. So maybe, before this I forgot to explain. So here, remember in your car or in your radio, when you want to listen to a specific radio station, you are actually tuned to that frequency band. Okay, so the tuning process, the tuning frequency is actually the center frequency of the entire bandwidth that you want to choose. Okay, so actually from the beginning, from the beginning here, when I want to listen to radio station A, for example, radio station A has a frequency of A hertz, for example. 1 megahertz, for example. Maybe we can use this one. Okay, 1 megahertz, for example. Okay, so pre-selector will select the band frequency center at 1 megahertz. Okay, and this again, this consists of a few channels. Okay, maybe channel, the one that I want to listen, and the other channel that I don't want to listen actually. Okay, so for example, this is channel 1, channel 2, channel 3. I only want to listen to channel 1 center at 1 megahertz. So this will be down convert into IF. Okay, down convert into IF. Again, we still have the same bandwidth, but center at 455 kilohertz. This is channel 1, channel 2, and channel 3. After down convert into IF, then it goes through the IF bandpass filter. So that's why IF bandpass filter will tune to the center frequency of this band. So I want to listen to since the beginning actually we already tuned so that means the bandpass filter in the IF section will tune to the center of 455, and this bandpass filter has a bandwidth of a certain portion, for example a few kilohertz. So that a few kilohertz of bandwidth enough to select only one channel. Okay, and remove the others. So I get channel 1 at the end of the process. Macam mana ini berlaku? So it's a good question for you to ask. There's an example about this. Okay, I will show you later about the example. Akan ada example tentang ini. Okay. This example. So you ask me question before I explain about this. Okay, kamu sudah tanya saya soalan seperti dalam example ini. So this is actually example from the Wayne Thomas's book. Okay, so this is related to your question, the question that you asked previously. Okay, so let me explain again about it. So this you can get this from the Wayne Thomas's book. So I snap a picture about this and I put inside the lecture notes. Okay, so ini ada dalam Wayne Thomas's book, chapter 5. Okay, figure 5.5, which is chapter 5. Okay, so let's look from here. So this is the picture of a receiver up to the IF section. Okay, up to the IF section. So you see that the receiver received the AM signal. It is capable to receive 535 until 1605. So this is the AM frequency band or the RF signal. Okay, so previously I mentioned 17 something. So there's a different AM frequency band. Some of the frequency band is within this range. So AM frequency band by standard has a few sets. So one of it is between 535 until 1605 kilohertz. Okay, so this AM frequency band consists of many radio channels. Many. How many? It depends. Okay, we need to know how much is the bandwidth for single channel, then we can calculate the total available channels. That one is later you're gonna see for the FM later. So this is from the antenna. Okay, antenna receive this frequency band, very big. Okay, and then pre-selector in this example select only from 535 until 565. Okay, so in this example actually we want to tune to channel 2, which is at frequency 550. Okay, so I want to listen to radio 550 kilohertz. Okay, and my pre-selector has a bandwidth of 30 kilohertz in this example. I want to listen to radio station 550 kilohertz, and my pre-selector tuned at 550 kilohertz, and this pre-selector has a bandwidth of 30 kilohertz in this example. Okay, so within this 30 kilohertz there are about 3 channels. Okay, this is just example. Ini cuma example. It doesn't mean that it needs to be 3 channels. It does not mean that it needs to be 3 channels, but in this example it consists of 3 channels. So within the 30 kilohertz of pre-selector band, it selects a small portion of the bandwidth which consists up to 3 channels. Okay, so channel 1, this one, channel 1, channel 2, and channel 3. And I want to listen to this radio channel actually. Okay, it explicitly mentioned here that we want to tune to channel 2. When we tune to channel 2, that means we tune to the word tune, that means you tune your radio, you tune your radio to that frequency. Okay, the word tune kat sini adalah bermaksud kita tune kita punya radio tu pada frekuensi tersebut. We tune our radio at that frequency. And when this happen, that means the center is at 550. This pre-selector has a bandwidth of 30 kilohertz in this example. So within 30 kilohertz, so there's a 3 channels. Okay, and I want to listen to this channel only. Okay, so what happened? So after the pre-selector, so you see that pre-selector limits from bigger bandwidth, from bigger bandwidth 535 until 1605. So pre-selector only limits this amount. and it still consists of 3 channels. We need to do another process so that we can get single channel. So what happened later is that goes through the mixer converter section. Mixer converter will down convert the frequency into intermediate frequency, and to do this, you see that it mixes with the local oscillator frequency. Local oscillator frequency is 1005 kilohertz, and if you see from here, it is larger than the RF frequency band, larger than the RF frequency band. So this is actually high side injection, high side injection, because the frequency is larger than the RF frequencies. RF frequency is between this 535 until 565. Okay, the RF frequency that has been selected by the pre-selector. Okay, so what happened? So if this is a high side injection, that means we can use this equation. Okay, we can use this equation. Okay, so we can find the FIF to be equal to FLO, sorry, FLO minus FRF. Okay, so every FRF will be converted into FIF. Setiap FRF akan ditukar kepada F intermediate. So what happened? So you see that we have how many frequency over here? We have 1, 2, 3, 4, 5, 6, and 7 frequencies. 7 RF frequency, related frequency. The upper center, we need to convert the lower, center, and upper frequency band. Okay, so what happened? You see that from here, the first line here. FLO minus 535. Okay, the first one here. We get 570 kilohertz. And then FLO minus 540. Okay, 540. We get 465 kilohertz. And then FLO minus 545 kilohertz, we get 460 kilohertz. So this is actually for channel 1. Okay, and then FLO minus FRF minus 550, we get 455 kilohertz. Okay, and here FLO 1005 minus 555 kilohertz, we get 450 kilohertz. So this is actually for channel 2. And then FLO 1005 minus 560 kilohertz, we get 445 kilohertz. And then 1005 minus 565 kilohertz, we get 440 kilohertz. And from here you see that we get new frequencies. Okay, we get new frequencies from 440 until 470, which are the intermediate frequencies. This one. Okay, so you see that we down convert from high frequency into intermediate frequency, lower frequency. Okay, and what happened actually? Okay, if you see from here, when we down convert, it looks like the channel has been swapped. The upper and lower channels has been swapped. You see that channel 1 is here, channel 3 is here, and channel 2 is here. Okay, so this is intermediate frequencies. Okay, so this is done by the mixer converter. Mixer converter convert into intermediate frequencies. Okay, so we still have 3 channels, the bandwidth is still the same for about 30 kilohertz. The bandwidth is still the same, 30 kilohertz. Okay, similar with the RF bandwidth in this example. Okay, so we get 3 channels, and remember that we want to listen to this radio station. Okay, so what happened? So in order to listen to channel 2 only, we need to do another process. We need to pass through the IF section. So IF section consists of IF filter and IF amplifier. So this is the question that you asked previously. Okay, so we put inside the IF section, it goes through the IF filter, the bandpass filter. So the bandpass filter, that means needs to be tuned to 455 kilohertz. Okay, so when the bandpass filter tuned at 455 kilohertz, and the bandpass filter must have a bandwidth of 10 kilohertz, so that it can select only channel 2, a single channel. Okay, so in this example, we tune to 455 kilohertz. Okay, and the IF filter has a bandwidth of 10 kilohertz, so it will select only this portion of channel. Okay, so we, at the end of the IF section, we produce only single channel, which is channel 2. Okay, so the output here will goes through the amplifier and then goes to the detector section. So detector section will do the demodulation process. Okay, so that means here is 455 and 455, and then here, so this is 460, 460. So I will show you what happened after this. It means this is 450, sorry, 450, 450, 455. Okay, so what happened is that it will be passed through the demodulator. Demodulator will convert into modulating signal frequency. Okay, it will down convert, it will demodulate into original frequency band. Okay, so this is a reverse process of the modulation. Okay, it will produce a modulating signal frequency at the output of the receiver. Okay, so you see that the demodulation process does not happen directly. Okay, from the RF frequency band down convert into intermediate frequency, then it will be passed through the demodulator. Within the IF section, it will select only a single channel, and this single channel will pass to the detector section, which will do the demodulation process to get the original output signal. Okay, so any question about this you can ask. Ada soalan tak?
No, Doctor.
Okay.
Clear.
Okay, so if you don't have question, I will move to the next slide. Okay. Again, this is example from Wayne Thomas's book. Okay, from Wayne Thomas's book. Okay, so figure 5.6, example 5.3. This is from Wayne Thomas's. This picture is about this example, 5.3. So for an AM super heterodyne receiver that uses a high side injection, has local oscillator frequency 1355 kilohertz. Okay, determine the IF carrier upper side frequency and IF lower side frequency for an RF wave that is made up of carrier and upper and lower frequency of 900, 905 and 895 kilohertz. Okay, so you see that here the RF frequency is given as this one, 900. So that means if you draw again, I like to draw like this. So this is 900, this is 905, this is 905, this is 895. Okay, this is frequency. So how much is this one, center upper side frequency USF, and here is this one. Okay, so the mixer converter has down convert this frequency band, and then so research injection. Okay, so the question asks how much the value of this after the mixer converter process. Okay, given the local oscillator frequency is 1355 kilohertz. Okay, so that means when we want to find the FIF, as in the previous example, FIF is equal to FLO minus RF. Okay, FLO minus FRF. So you get intermediate frequency. So you need to subtract all the RF frequencies. For example, here, when we want to find the center IF, it is equal to local oscillator frequency minus FRF center. So this is actually FRF center at 900. Okay, so we get 455 kilohertz. And then what? In order to find the upper side frequency, we need to subtract with the lower frequency of RF. Okay, so that means local oscillator frequency minus the lower frequency of RF, which is 895. So we get 460 kilohertz. And then what? FIF lower side frequency we get by subtracting the local oscillator with the upper frequency of RF. So we get 450 kilohertz. Okay, so that means the frequency band that we get is from 450 until 460. Okay, so this is from 450, 455 and 460 kilohertz. Okay, so this kind of this example has been asked previously in the final exam. Pernah ditanya dalam final exam. Almost same question like this. Okay, it is part of the final exam. It is one of the subsection question. Sub question. It is part of the sub question. So we have asked the student to find the lower side frequency, upper side frequency, and the center of IF. Pernah ditanya. We have asked this previously. Okay. So see that, note that the side frequency undergoes sideband reversal during the heterodyning process. So we already seen this process before. Reversal, that means in order to find the lower frequency, we need to subtract with the upper frequency of RF. Similar with the previous example, channel 1 and channel 2 becomes change side, F1 and F3 in the previous example. Okay. Okay, so you can read this frequency. This is commonly called sideband inversion. Sideband inversion is not detrimental to me. Okay. So this explanation has been explained in the Wayne Thomas's book. Okay. You have question about this, you can ask. Otherwise, I will move to the next slide. Okay, kalau ada soalan boleh tanya. Otherwise, saya akan teruskan. Image frequency. Okay. So, image frequency. Image frequency is any frequency other than the selected radio frequency carrier, if allowed to enter the receiver and mix with the local oscillator, will produce cross product frequency that is equal to the intermediate frequency. You have learned about cross product in chapter 2. Okay, ada diajar dalam chapter 2 cross product. Okay, remember cross product is remember in chapter 2 MF1 plus minus and F2. Okay, so the cross product. So if the cross product equal to the intermediate frequency, so it will produce image frequency, which is not good. Remember that we should block the image frequency from entering into the system. Okay, kita perlu kita perlu asingkan image frequency ni pada peringkat awal. Okay, so the preselector or the tune circuit is responsible to remove the image frequency. Okay, so the preselector or the tune circuit is responsible to remove the image frequency, because if the image frequency goes through the system, the receiver will unable to differentiate the desired frequency band. Okay, so it's gonna be a big problem. Okay, so you see that from this picture, image is located at this one. Image is located at 2 times the intermediate frequency from the RF frequency. Okay, 2 times the IF. So we should not allow this frequency band to enter we should not allow this frequency into the system. Okay, so this is, you see that this is like an image. Okay, so the distance is the same here. The distance is the same, FIF. Here is also FIF. Okay, so it is like a mirror. Okay, this is image is like a mirror to the RF frequency. Okay, so mathematically for high side injection, we can calculate the image equal to FLO plus FIF, or F image equal to FRF plus FIF. So either one is okay, either one is correct. Okay, you can use either of these. Okay, so FRF plus, okay, so you can get the image frequency. So this is also a common question in the final exam to find the image frequency. Okay, we're gonna see the example later about the image, about this one. So determine the image frequency for a standard broadcast band receiver using 455 kHz of intermediate frequency and tune to station at 620 kHz. Okay, so you already been provided with the intermediate frequency, and you already been provided with the RF frequency. Tune to the station. Okay, when you tune to a radio frequency, when you tune your radio to a certain frequency, that frequency is FRF. Okay, so we want to find the how much is the image frequency. So you can use any of the two equations given in the previous slide. So you can actually find using this equation, F image equal to FRF plus 2 times the F image. Okay. In this example, it tries to find the FLO first. Okay, FLO is equal to FRF plus F intermediate frequency. So you can find the FLO equal to 1075. So from here, it minus with the the image is located at local oscillator frequency plus image plus the FIF. So you get the image frequency. So this one is a bit complicated, is it? So you can actually find using this equation F image equal to FRF plus 2 times F intermediate frequency. Okay, so it is 620 kilohertz plus 2 times 455 kilohertz. Okay, so if you use a calculator, 455 times 2 plus 620, so you get 1530. Okay, so either equation you can use either formula, is okay, no problem. Okay, tidak ada masalah untuk menggunakan salah satu daripada formula yang diberikan. Either formula for the image calculation is okay, no problem. You can use this equation, or you can use this equation by finding the local oscillator frequency first. Okay, so this is remember this LO should be the subscript. Okay, so you get the image frequency. Ini ada soalan. If you have question, please ask. Otherwise, I'll move to the next example. Okay, and again, I repeat again. It is the job. It is the responsibility of the pre-selector or the tune circuit to remove the image frequency. Okay, and if I go back to the picture here, wait. I go back here. So this pre-selector must remove the image frequency. Okay, otherwise there's gonna be interference within the signal. Okay, so I go forward. This one, image frequency rejection ratio, IFRR. This also a favorite question in the final exam. We have asked this many times. Almost every semester we will ask this question. Okay, hampir setiap semester kita tanya. Okay, so there are we need to find the IFRR, image frequency rejection ratio, which is equal to first we need to find the image rejection alpha parameter, which is equal to square root of 1 plus Q square rho square. Q square is the quality factor of the tune circuit. Rho square is the rejection ratio, which is equal to F image divided with FRF minus FRF over F image. This one, Okay, so F image divided with FRF minus FRF over F image. So rho parameter has no unit. Similar with Q parameter, there's no unit. Okay, and again remember for the Q parameter is equal to inductive reactance divided with the resistance, or the resonant frequency divided with the bandwidth of the tune circuit. Okay, you can find the Q parameter as in the previous slide. Okay, and when you want to measure the IFRR in decibel, it is 20 log of alpha. Okay, 20 log of alpha you get in terms of decibel. Okay, so normally careless mistakes by the student. Student tend to do careless mistake at this part. Okay, sorry, to find the alpha, to find the alpha, student tends to do careless mistake. Okay, my suggestion is to make bracket like this, so that you are not doing the careless mistakes. Okay, saya cadangkan buat bracket supaya tidak melakukan careless mistakes. Okay, and if you want to see the example, this one, from the previous example, calculate the image rejection in decibel, assuming that the input filter consists of tuned circuit Q parameter of 40. Remember, in the previous example, we get 1530, this one. We already get image frequency as 1530 kilohertz. Okay, so 1530 is from the previous image, F image. Okay, so we can find the IF image rejection ratio in decibel. First, we need to calculate the rho parameter, which is F image over FRF. FRF also from the previous example, okay, from example 2.12, FRF is equal to 620 kilohertz from the previous example. Okay, so we get here rho parameter F image over FRF minus FRF over F image, so we get 2.0625. And then from here we can find the alpha parameter equal to square root of 1 plus q square rho square. So this is equal to 1 plus square root of 1 plus 40 square, the q square, multiplied with rho square, 2.0625 square, and the square root, so we get it 82.5061. So since the question asks about decibel, so you need to proceed until you get this one. So 20 log alpha, so you get 20 log 82.5061, so you get 38.33 decibel. Okay, so this is the IFRR. So any question you want to ask about this example? Kalau ada soalan boleh tanya. Okay. Any question? No question? If no question, betul tak ada soalan you are most welcome to ask question. If you don't understand, please ask question. I will explain again, no problem. Okay. Okay, so if no question, I move to the next slide. Okay. So up to here, we already finished AM topic, which is the first part of chapter 3. Now we want to look into the second part of chapter 3, okay, which is the angle modulation. So siapa yang mengantuk, you can make your own exercise. Okay, maybe you want to go to the toilet, maybe you want to go to somewhere, it's up to you. But I need to continue. I need to continue. Okay, the second part is angle modulation. Remember, angle modulation consists of frequency modulation, FM, and also the phase modulation, PM. Both of these are interrelated. Okay, they are connected to each other. So you're gonna see the relationship between both of these. So as I mentioned previously, that both of these is like a twin brother. So if you change one parameter, the others will change. Okay. Angle modulation. Okay. So remember angle modulation. For example, like frequency modulation. Frequency modulation is the process of changing the frequency of the carrier in accordance with the amplitude variation of the input message. Okay, there's a FM. And phase modulation is the process of changing the phase of the carrier in accordance with the amplitude variation of the input message. Okay, so the general equation for angle modulation for both FM and PM is given as Vc sine 2 pi fct plus theta t. Okay, So this is general equation for FM and also for PM, both of it. Okay, general equation for FM and PM. Okay, and you see that a bracket here. Make sure you do the bracket like this, and be careful, okay, because everything here belong to the sine function. Okay, if you don't do a bracket like this, your equation is wrong. Okay, so I always suggest to the student, I always suggest to the student, when you want to write the equation, I suggest you to write a big bracket like this, so that you know that everything here is under the sine function. Okay, so in the previous semesters, a careless mistake by student is like this. Student do like this. Sorry. Wait. So student tends to do like this, plus theta t. So this is careless mistake. When you do the calculation, you will get the wrong answer. Okay, if you do like this, you will get the wrong answer. Okay, what you need to do is you must put the big bracket. Okay, so from this general equation, only the theta parameter will change. Okay, theta t is a function of time, which consists of a modulating signal. Okay, theta t is a function of modulating signal. It consists of modulating signal. Okay, and VMT, again we use sine wave. Vm sine 2 pi FMT. Okay, and for your information, if you read from other literature books, because the sine function is from Wayne Thomas's book. If you read other literature books, you will find that they're gonna use cosine. Okay, other literature book use like this, BC cos 2 pi FCT plus theta t. No problem. Okay, either sine or cos, it's not a problem. Okay, tidak ada masalah. Okay, and again, some other literature books also use cosine for VMT. So no problem, tidak ada masalah. Okay, there are gonna be example about this, sine and cos. Okay, so based on the general equation, we can determine 4 different parameters, what we call as the first instantaneous phase deviation. Instantaneous phase deviation is the instantaneous change in the phase of the carrier at a given instant of time and indicates how much the phase of the carrier is changed with respect to its reference phase. Okay, so instantaneous phase deviation is the current phase. Okay, is the phase variations according to the input. Okay, so it is equal to theta t radians. Okay, which is here theta t radian. So what we want to analyze is this part. Okay, we want to analyze this part. Okay, instantaneous phase deviation is this one, theta t. Okay, and if you see, instantaneous phase is the precise phase value of the carrier at a particular time. Okay, at the instant time. That means the exact value of the phase at a specific time. This is what we call as instantaneous phase. Nilai fasa pada satu-satu masa. Okay. Instantaneous phase deviation is the phase deviation at a certain period of time. Instantaneous phase is the exact time. It's the exact phase of the carrier at that specific time. Okay, so we get omega ct plus theta t in terms of radians. Okay, and if you go back to this example, so this whole thing is the precise phase. Okay, is the is the carrier phase. Sorry, is the instantaneous phase. Okay, the whole parameter here is the instantaneous phase. Okay, the third parameter is what we call as, so this is the third parameter, fourth parameter. This one is 2 seconds. Okay, so the third parameter is what we call as the instantaneous frequency deviation, theta prime t. Okay, so theta prime t is the deviation of d over dt, deviation of theta t. Okay, so pembezaan kepada theta t, you will get theta prime t. Okay, so theta prime t, the unit is radian per second. It is defined as instantaneous change, kadar perubahan. So the instantaneous change of frequency. Previously is the instantaneous change of phase. Now is the instantaneous change of frequency of the carrier. Okay, as defined as the first derivative. Okay, so therefore we can write that theta prime t is equal to a value in terms of radian per second, or you can call it cycle per second, or in terms of hertz. Okay, it is a radian per second or cycle per second or hertz. Okay, and then the fourth parameter is the instantaneous frequency, the precise frequency of the carrier at a specific time. So you need to do the first derivative of d dt of omega ct plus theta t. Okay, so you get omega c plus theta prime t. Okay, first derivative of theta t, you will get theta prime t. So this is in terms of radian per second or in terms of hertz. Okay, same. So you see that okay, so this is to substitute the 2 pi fc. So when we substitute the 2 pi fc to the omega, okay, omega is 2 pi f. So we get 2 pi f plus theta prime t. So this is actually previously is omega c plus theta prime t. So 2 pi fc plus theta t. Okay, so therefore phase modulation can be defined as the angle modulation in the phase deviation theta t. So you can read this one. I have explained about PM and also FM. Okay, PM is a phase modulation, is the process of changing the phase of the carrier in accordance with the PM is the phase modulation, is the process of changing the phase of the carrier in accordance with the amplitude variation of the modulating signal. Frequency modulation FM is the process of changing the frequency of the carrier in accordance with the amplitude variation of the input message. Okay, and here is another parameter, what we call as the deviation sensitivity, which is Kp and Kf. Okay, Kp and Kf are constant parameter, what we call as the deviation sensitivity parameter for the phase and frequency respectively. So Kp is the phase deviation sensitivity parameter. Kf is the frequency deviation sensitivity parameter. Okay. So when we want to find the theta t and theta prime t, okay, so theta t can be defined as Kp Vmt. Theta prime t for the Fm is equal to Kf Vmt. Okay, so theta t radian, theta prime t radian per second. Okay, so what is Kp and Kf? Okay, so Kp, the unit for Kp is radian per volt. Okay, so this is the unit for Kp, radians per volt. Okay, so how does we want to find the Kp? Kp is found by the difference of theta, okay, divide with the difference of voltage. Okay, delta theta divide with delta V. Whereas for Kf, it is the unit is radian per second per volt. It is calculated by delta omega divide with delta V. Okay, so we have asked this question in the previous semester final exam, where we give student a table. Okay, kita pernah beri table seperti ini I'm not sure whether Kp or Kf. Let's say we want to try to find Kf, for example. So we give the value of omega, okay, and also the value of voltage. So this is based on the measurement, okay, and we give you the value like this, for example. So x1, x2, x3, y1, y2, y3. Okay, so in order to find Kf, Kf is equal to delta omega, the difference of omega divided with the difference of voltage. So this is, you can do like this, x2 minus x1 divide with y2 minus y1. Or you can also find like this, x3 minus x2 divide with y3 minus y2. You'll get the same answer. Okay, so you can find the Kf parameter. Or maybe Kp. Kp, if you are given in term of theta, if you are given in term of theta, okay, so theta, for example, and also the voltage. So this is x1, x2, x3, similar, y1, y2, y3. Okay, so if you want to find Kp, Kp is equal to x1 minus x2, or x3 minus x2 is also similar, y1 minus sorry terbalik yeah. So this is so x2 minus x1 and also y2 minus y1. Okay, or this is x3 minus x2 divide with y3 minus y2. Okay, so you get the value of Kp. Kp, the value is radian per second. The unit is radian per volt, and Kf is radian per second per volt. Okay, and again this one if you want to find the theta prime t, again as I mentioned previously, it is the first derivative of theta t. Okay, and if you want to find theta t, that means you need to do integral process. So theta t is integral of theta prime t, which is equal to Kf Vmt. Okay, so you can put outside Kf because this is a constant parameter, and you can do the integral for Vmt. So how does it can find this value? Okay, Kf Vmt is from this one. Okay, Kf Vmt is for theta prime t, Kp Vmt is for theta t. Okay, so it it's replace theta prime t with kf vmt, and then we can do the integral. Okay, theta prime t is equal to kf vmt. Okay, so we can find the complete equation for PM and FM. Okay, so for phase modulation, again we from the general equation, so this is the general equation, Vc sine omega ct plus theta t. And for the phase modulation equation, it is become Vc sine omega ct plus, so we can change theta t into kp vmt, which is sine omega mt. So this is 2 pi fm t. Okay, so this is the equation for phase modulation. Okay, this is the general equation for phase modulation, PM. Okay, what about the equation for FM? This one. Okay, so the equation for FM is like this. From the general equation, Vc sine omega ct plus theta t, and then this is actually 2 pi f ct, okay, omega ct or 2 pi f ct. Okay, and then theta t is equal to integral of theta prime t. Theta prime t is equal to kf vmt. Okay, so we can do the integral of vmt by put outside the kf and vm, because kf and peak amplitude is a constant parameter. You can put outside, and then you can do the integral of sine omega mt. Okay, so this one is become sine omega become negative cos. Integral of sine, you will get negative cos, divide with omega m. Okay, so if you want to do like this is also okay. For example, this one, so Vc sine in bracket 2 pi f ct plus kf vm integral of sine 2 pi fm t dt. Okay, and then close bracket. So here you can rewrite this one to become Vc sine 2 pi f ct plus, so kf vm, so this one becomes, so this integral of sine, you will get negative cos, so this is supposed to be negative. Okay, so negative kf vm over 2 pi fm cos 2 pi fm t, close big bracket. Okay, so I just change the omega with 2 pi f. Saya cuma tukar omega kepada 2 pi f. Okay, so now you get the equation for FM, frequency modulation. Okay, and this is the equation for PM. Okay, so you get the general equation for FM and PM. Okay, so previously we have asked the student to derive the equation to be like this. We have asked this kind of question previously. Okay, so we give the value here, so find the FM equation. Okay, so you can use the this process, integral process, to find the final answer. Okay, pernah ditanya soalan seperti ini. So it is not difficult, it's just integral of sine or integral of cosine. Simple. Okay, tidak susah. Exercise 3.1. So derive the PM and FM signal using both cosine wave signal. Okay. So this time it uses a cosine. Okay. You see that you are given general equation as a cosine. Okay. And then general equation for a VMT is equal to Vm cos omega mt. Okay. So you can find the PM and FM signal. Remember from the general equation we can define the PM equation. PM equation is very simple. You just need to change theta t with Kp Vmt. Okay, so it becomes Vc cos omega Ct plus Kp Vm cos omega Mt. Okay, and then what? For the frequency modulation, okay, for the frequency modulation, you can find the equation by integral of Kf Vmt. Okay, so Kf Vmt, so Vc cos omega C plus integral of Kf Vm cos omega Mt. So this is Vmt, Kf Vmt. So this becomes integral of cos, you will get positive sign. Okay, so Vc cos omega Ct plus Kf Vm over omega m sine omega mt. Integral of cos, you will get positive sign. Okay, so this is actually like this, Vc cos big bracket 2 pi f fct plus Kf Vm over 2 pi fm sine 2 pi fm t, close big bracket. Okay, Kf Vm sine Kf Vm over 2 pi fm. Ini tak jelas, mungkin saya jelaskan balik sekejap. So plus Kf Vm over 2 pi Fm sine 2 pi Fm t, close big bracket. Okay, similar with this one. I just changed omega with 2 pi f. Okay, and then what? So now it's a heavy rain at my place. Dekat tempat saya sekarang hujan lebat. So you can hear, maybe you can hear the sound of the raining. Okay. Okay, so up to here, and then what? This one. So if you see from the for FM, okay, this is for the frequency. You see that for the FM and PM, what happened is that during the process, the frequency and phase will change in accordance with the amplitude variation of the input. Okay, so if you remember again what happened in the amplitude modulation. So amplitude modulation, the amplitude of the carrier change up and down. Okay, but in the FM and PM, the amplitude is not changed. Only the frequency of phase will change in accordance with the input. Okay, so you see that from here, you see that how does the wave looks like? So you see that the changes. What happened? So the carrier frequency will move from Fc to Fc plus delta f, the maximum frequency. Okay, when the amplitude move from 0 until the maximum peak amplitude, V peak. This is the input. This is a Vm peak. Sorry, I will. This is a Vm peak. So when the amplitude is maximum, the carrier frequency will be maximum. Okay, in this example. And then when the information signal, when the modulating signal change polarity into V minus Vm peak, negative peak, so what happened? This is a negative peak, Vm peak, so what happened is that the carrier frequency will change to the lower frequency, which is Fc minus delta F. Okay, so delta F, this delta S is the frequency deviation. Okay, is the carrier frequency deviation. Delta F is the carrier frequency deviation. So you see that this is the limit of the carrier from Fc minus delta F until Fc plus delta F. So the frequency keep on changing, from Fc plus Fc plus Fc until Fc plus delta F, the maximum, and then move from Fc until Fc minus delta F, the minimum. So now the frequency is changed. Remember, if we change the frequency, we are indirectly change the phase of the carrier as well. Okay, kalau kita tukar frequency carrier, secara tak langsung kita sebenarnya menukar fasa carrier. Okay, and delta F is the frequency deviation for the carrier. 2 delta F is what we call as the carrier swing. Okay, carrier swing. Okay, this one. This is very good. Okay, I have some time to explain. So I will explain. So you see that from this picture, okay, the first graph here is the carrier frequency signal. Here is the modulating signal frequency, modulating signal, and then here C is the frequency. This is FM. This is PM signal. Okay, so you see that FM and PM signal looks similar. Okay, if you are not given A and B, okay, if you are not given figure A and B, you cannot determine whether this is FM or PM. Okay, we cannot determine whether this is FM or PM without having the carrier signal wave and also the modulating signal wave. Okay, we need both of these A and B so that we can differentiate between FM and PM. Okay, so you see that for FM, okay, the critical change happen when the modulating signal frequency achieve the maximum amplitude, either maximum positive or maximum negative. So you see that the maximum here, you see that initially here from 0, so initially the carrier frequency is at rest frequency. Rest frequency is the same frequency as this one, original frequency, rest. Okay, and then when the modulating signal frequency move when the modulating signal move to peak amplitude, what happen is that the frequency of the carrier becomes minimum, which is maximum minus deviation. So over here at this point, okay, at this point the carrier frequency is minimum, Fc minus delta F. Okay, and then the modulating signal move towards 0 crossing or the x-axis. What happened is that carrier frequency is at Fc, rest. So initially rest is Fc, and then the modulating signal moves to negative peak. Okay, negative peak. So what happened is that the carrier will undergo maximum positive deviation. That means the carrier will be at its maximum value, which is Fc plus delta F, and then move to the 0 crossing or x-axis. It becomes Fc rest. Okay, so this is for the happen to the phase modulation. So phase modulation, what happened is that the critical change is during the zero crossing. Previously for FM, critical change happened at the peak amplitude of the modulating signal. Okay, but for PM, phase modulation, critical change happened during the zero crossing of the modulating signal. So you see that from here, initially at rest frequency Fc, and then here you see that this is starting. So this is the wave move from 0 towards maximum. Okay, it moves from 0 until maximum positive. So the frequency of the carrier becomes maximum Fc plus delta F. Okay, and when the I erase this one. Wait. So when the wave achieve the maximum peak amplitude, what happen is that the output Fc will be at rest frequency. And when the modulating signal goes through the zero crossing, so this time zero crossing from positive towards negative cycle. So what happen is that the output will be at negative maximum negative deviation, means that Fc carrier frequency would be at minimum, which is Fc minus delta F. So kalau turun, dia akan jadi Fc minus delta F. Okay, if it is go down, it's gonna be Fc minus delta F. And you see that the wave moves towards negative peak amplitude. So what happened is that carrier would be at rest, which is Fc. And then modulating signal move towards another zero crossing, and this time it moved from negative to the positive. And what happened is that the carrier frequency would be at maximum, which is Fc plus delta F, and so on, dan seterusnya. Okay, so the key point here is that frequency modulation, the critical change happen when the modulating signal achieve the peak amplitude. Okay, either peak positive or peak negative. Okay, perubahan kritikal berlaku ketika modulating signal mencapai nilai peak positif ataupun peak negatif. This is for the frequency modulation. But for the phase modulation, the critical change of the signal happens when the modulating signal cross the x-axis. Okay, perubahan ketara pada frequency phase modulation adalah pada ketika modulating signal itu cross the zero crossing, either from negative to positive or positive to negative. Okay, so we have asked this kind of question in the previous exam, where the students needs to know whether this is FM or PM. Then you can calculate the other parameters. Okay, then you can determine the other set of parameters. Okay, and in order to know whether this is FM or PM, you need to have the reference carrier and also reference modulating signal. And if you see from this graph, you see that the amplitude of the carrier does not change for the FM and PM. It remains the same, only the frequency and phase are changed. Different from the AM. Okay, kalau AM, the amplitude of the carrier change. Okay, so that's all for today. Okay, that's all for today. We will continue again next week. Sorry, next week is a semester break. Next week is a semester break. So I will see you again after the semester break. Okay, so happy holiday to all of you, and happy Hari Raya. Selamat Hari Raya. So we can take the attendance now. After the attendance, you can go out. You can go anywhere you like. Okay, so open your QR code. So you can scan the attendance. Attendance. Okay, you can scan. Okay, so selamat Hari Raya and happy holiday to all of you.
Selamat Raya Doktor, thank
Okay,
you.
selamat Raya.
Selamat Hari Raya Doktor, thank you.
Okay,
Thank you,
welcome.
Doktor.
Selamat Raya.
Thank you, Doktor.
Okay,
Hari
welcome.
Raya.
Selamat Raya.
Doktor.
Okay, welcome.
Thank you Doktor.
Okay, welcome.
Thank you, Doktor.
Selamat Hari Raya.
Doktor, saya tak boleh scan.
Siapa nama?
Nur Nadia.
Nurul Nadia. Okay, done.
Doktor, saya pun
Doktor, selamat raya.
Okay, selamat Raya. Siapa tadi?
Muhammad Amirul Haziq.
Muhammad?
Amirul Haziq, Doktor.
Okay, done. Okay, dah.
Okey, Doktor. Doktor Irfan Adi.
Siapa? Irfan.
Dah boleh.
Ni Irfan dah. Siapa lagi?
Ahmad Samir.
Samir? Ahmed Samir. Okay.
Asadi Hazin, Doktor.
Okay, Al-Asadi. Okay.
Thank you.
Okay. Where is Akmal? Akmal ada? Akmal, are you there? Akmal tak ada Ni Syahmi dah ni. Syahmi dah take Akmal missing So okay, that's all for today.